Socratic Math Tutor here. Happy New Year. So here's the first few prime numbers. We've got 2, 3, 5, 7, 11, 13, 17, and 19. And what I want to talk to you guys about today is a conjecture I've been sitting on about the prime numbers. I've been sitting on it for about 5 years. I've never written it up or published it in a journal or anything like that. But I've got this conjecture, and it's really about the size of these gaps, right? So the gap between 2 and 3 is 1. After that, we hit 2. Then we've got 2 again. Then we hit 4. Back to 2. The gap between 11 and 13 is 2. Then 4, and then 2 again. Right, and so there's this sort of strange pattern of gaps between prime numbers. And there's this open problem about, well, where are these gaps coming from, and how do we calculate them? And why are they what they are? So this is generally considered quite a hard problem. There's not a whole lot of structure in this sequence of numbers. It does seem to be quite pseudo-random in a lot of ways. But I've actually got a conjecture that I'm going to show to you guys that actually lets you calculate the size of these gaps. And I can't prove it works. It's just a conjecture. If someone in the audience can prove it, that would be amazing, but I can't guarantee it works. What I can guarantee is that it works for every number I've tried, except for 3. So it doesn't work for 3, it doesn't give you the right prime gap at 3. It miscalculates this number. But for every other number I've tried, up to several thousand, it gets us the right prime gap. So hopefully that's pretty cool. And hopefully you guys will find this one interesting. Now, you're probably familiar with raising one number to the power of another. So, 5 cubed is 5 times 5 times 5, for example. And for the purposes of this conjecture, we need to look at a variant on this operation. And so what it's called the Rising Factorial. We basically put an arrow before the superscript, so an upwards arrow. And what we do is it starts the same, but we actually increase the number on each step. Right, so 5 rising factorial 3 would be 5 times 6 times 7. Now there's another operation here that we're actually not going to use, but you should probably know about. So that's the falling factorial, and so basically we just reduce the number each time. Right, and so 5 falling factorial 3 is 5 times 4 times 3. And so that means, for example, that we can always define n factorial as being equal to n falling factorial n. Right, so it's kind of like n to the power of n, but each term is getting successively smaller by 1. So that's rising and falling factorial. We're not actually going to need falling factorial for this conjecture. So what we're going to do is we're going to focus in on the rising factorial. And it turns out that there's some really interesting connections between rising factorials and prime gaps. So we'll proceed as follows. Let's define that n pop factorial equals the maximum number, call it r. It's got to be a whole number, so I'll write z greater than or equal to 1 for that, with the property that n rising factorial r is a factor of n factorial. Okay, so let's just go over what all this notation means. This refers to the whole numbers, so 1, 2, 3, etc. This is the rising factorial. It's this thing that we talked about back here. And this line means is a factor of. Is a factor of. So let's compute an example. So let's find 5 pop factorial. And by definition, this is just the maximum number r in the positive integers, with the property that 5 rising factorial r is a factor of 5 factorial. So it has to be a factor of 120. Okay, so 5 rising factorial 1 equals, well, it's just 5, and that's clearly a factor of 120, and so we need to keep going. So now we compute 5 rising factorial 2, and this will be 5 times 6, which is 30. Okay, still a factor of 120. We'll go to the next one. 5 rising factorial 3 equals, well, it's 30 times 7, which is 210, which is clearly not a factor of 120. And so the maximum is clearly this one. Okay, so the maximum equals 2. So therefore, this thing we were trying to work out, which I'm calling 5 pop factorial, as defined here, this thing equals 2. And lo and behold, 2 is the jump to the next prime, because the next prime is 7. So this pop factorial thing, it seems to be connected to prime gaps, at least based on this single example. So to test out this theory, let's go ahead and write some code, and that way we can test some bigger numbers. So I've got VS Code open, and I'm gonna write it up in Python. So if you use Python, you can follow along. Otherwise, feel free to just sit down and do a few computations by hand and just see what you get. But this will help us test our hypothesis a lot more easily. So we'll start by defining factorials. We're going to give our factorial function a value x. We're going to return something called y. And we need to go ahead and calculate y. So what we'll basically do is for every number I in the range from 1 to x, we actually need x plus 1 here. And the reason is Python stops before the last item. So if we don't include x plus 1, then we'll stop before actually getting to x. So for I in range of 1 to x plus 1, we need y to be multiplied by I. And we also need to initialize y as 1. And so hopefully this will give us the right value. Let's go ahead and print factorial of 5. And as long as this is 120, we'll be pretty satisfied that we've done it right. So now I just need to save my file, call it primegaps.py. There's our console, and let's go ahead and run our program. And there we have it, 120. So it looks like factorial is working. Okay, so we don't need this line anymore. Let's go ahead and code up a Rising Factorial function. And this actually needs to take 2 arguments, right? So remember we were talking about 5 Rising Factorial, 3, stuff like that. So this will be the base, and this will be our exponent. Once again, we're going to return y after doing some stuff with an initial value. So we'll initialize it to 1, and then set up our loop right in the middle. So for I in range of x through to x plus n, what we're basically going to do is we're going to multiply y by that number I. So if all goes to plan, this should give us the right value for Rising Factorial. So print Rising Factorial, print 5 Rising Factorial 3. We did work this out earlier. We found that it was 210. And so hopefully, if all goes to plan, we'll get 210. And there it is. Okay, so let's go ahead and define a factorial pop function. And what we're going to do is we're going to just pre-compute x factorial. X factorial equals factorial of x. And right at the end, we're going to return an exponent. Okay, so we're going to return the greatest exponent such that the rising factorial is a factor of x factorial. And so to compute that, what we're going to do is we're going to start this exponent at 1. And then we're going to say while rising factorial of x comma n is a factor of x factorial, what we're just going to do is we're going to increase n. Okay? So we're going to keep increasing n until it's no longer the case that rising factorial of x comma n is a factor of x factorial, and then we're going to return n. And we actually need a -1 here, and the reason is because the first time this condition fails, we've actually gone 1 too far. So we've gone beyond the maximum that makes this condition true. We found one that makes it not true, and that's how we escape the loop. And so that basically means that n is 1 too high once we get to this line. And so that's why we need the n-1 here. Now, the other thing is, this is not actually correct Python notation because this pipe symbol does not mean is a factor of in Python. So what we're going to do is we're going to use the fact that A is a factor of B if and only if B reduced modulo A is 0. And so by using this expression, we can actually write our code using correct Python notation. So I'll put this on the left. I'll put a %. We're going to reduce x factorial modulo the rising factorial, and that should be 0. And if it is 0, then A is a factor of B, and if it's not 0, then it's not a factor. Let's go ahead and print factorial pop of 5. And hopefully this will be 2. As long as it's 2, we'll have a pretty good idea that our code is right. And there it is. It's what we expected. Finally, we'll go ahead and compute a next prime function. And all this is going to do is it'll return the number we give it plus the factorial pop. And the reason is basically that we're conjecturing that this factorial pop is actually the gap to the next prime. So if we return x plus the factorial pop, we should get the next prime number after x. So let's go ahead and actually test that theory, right? So let's go ahead and print next prime after 10. That should be 11. Let's go ahead and print the next prime after 11. That should be 13. Next prime after 12. That should still be 13. Next prime after 13. That should be 17. And let's go ahead and print those. And lo and behold, 11, 13, 13, 17. So here's the cool thing about that. I've tested it for really high numbers, and it always works, as far as I can tell. And I have no idea why it works. And furthermore, for some reason, there's a really small number for which it doesn't work. And that number is 3. I don't know why, but if we print next prime after 3, go ahead and execute that. So this algorithm thinks that the next prime is 4, which is totally not, right? The next prime after 3 is 5. So I have no idea why it works, and I have no idea why it doesn't work for this specific number. But I think that's over and out from me. Feel free to try and prove this conjecture or try and test it for some bigger numbers. I'm going to link the code here in the video description. One thing you might want to do if you want to test bigger numbers is actually improve this design, because we're repeatedly calculating Rising Factorial here for bigger and bigger values of n. And that's actually just not efficient. So you may want to rewrite this, maybe paste it in here. And just make some changes to do it a little bit more efficiently. And as long as you do that, you'll be able to test some pretty big numbers. Okay, so let me know if you do find a counterexample, and let me know if you come up with an idea for a proof. And it's over and out from me. So Happy New Year, and may 2022 be as exciting as this incredibly strange conjecture about prime gaps and factorials.